Okay, we'll get started. And so yeah, happy 10th week. Just a few more days left, and then you'll be in summer. Okay. All right. So we have two topics to cover today, and these will be hypothesis testing for mu based on one sample, and hypothesis testing for mu1 and mu2 based on two samples. All right, and so we'll cover this today. This will wrap up chapter 9, and then on Wednesday and Friday we'll spend some time in review. Come to class on Wednesday. I'll have there will be a lot of clicker questions going on Wednesday. Okay, just to kind of go through it. I posted a whole bunch of practice materials on CCLE. Okay, so you guys can study and get ready for the final exam. I'll just do a quick, before we get into this stuff, let me just do a quick breakdown on the final. Okay, quick overview of the final. Okay. So what we'll have is approximately 10 questions on conceptual stuff. We'll say conceptual topics regarding statistical inference. Okay, then you'll have approximately 5 questions on checking conditions. You'll have about another 10 questions on kind of definition / conceptual topics from chapters 1 through 6. Okay, and then you'll have 30 to 35 questions doing statistical inference. So this would be chapters 7 to 9, confidence intervals and hypothesis tests. And that's pretty much the content of the final. So that's what I've got. That's what I've got planned. So approximately 55 to 60 questions, something around there, with this approximate breakdown here. Okay. So the 30 to 35 questions doing statistical inference. That's all. It's kind of like the quiz that you had, where the topics of that quiz were for proportions, but now it'll be proportions and means, and you're going to have confidence intervals, hypothesis tests, and all of those things are kind of broken out into, maybe 3 or 4 questions related to one given scenario. So I'll describe, the scenario, and then I'll have you know, 3 or 4 questions related to that. You know, like what are the hypotheses, what's the p-value that you find, and you know, what kind of conclusions you make, things like that. Okay, is this all good? And so on Wednesday we'll spend time going over kind of the conceptual topics for statistical inference. And then I think I posted some practice questions on that as well. All right, so anyway, back to hypothesis testing for mu based on 1 sample and mu1 and mu2 based on 2 samples. Okay, so everything here, again, just like when we did hypothesis testing for proportions, the breakdown is still the same, the 4 steps. So if you understood hypothesis testing when dealing with proportions, then everything for hypothesis testing with means should be easy to pick up. Okay, the biggest difference is that we use the t-table rather than the z-table. Okay, and so if you did not get a t-table last week, I have a few extra t-tables. So you can grab one. All right. So again, we have 4 stages. Those stages will be 1, make your hypotheses. 2, your preparation. 3 is calculation. And 4 is conclusion. Okay. And again, you know, if you misplaced your t-table, they are available on week 10. You can print out your own z and your own t-table. They are available. You will need to bring your own tables for the final. I will provide the formula sheet. Okay, so the formula sheet, that will be printed on the back side of the Scantron answer form. Okay, so that will be provided. Okay, so we'll start off with hypothesis testing for mu based on 1 sample, and we'll run through these 4 steps again. Okay, so we've got hypothesis testing for mu based on 1 sample. Okay, so when we set up our hypotheses, step 1, our hypotheses, you have your null hypothesis and you have your alternative hypothesis. The null hypothesis will be that mu is equal to some number mu0. Okay, so for example, you know, you might write that the null hypothesis is that mu is equal to 28. Okay, and then the alternative will be mu is not equal to mu0, or mu is greater than mu0, or mu is less than mu0. Okay, and then your choice of not equal, greater than, or less than depends on how the question is written. Okay. Now we will do our preparation step. So as far as preparation goes, we need to identify our data. Identifying the data, we need n, sample size, x bar, sample mean, s, sample standard deviation, and we also need a mu0, value from the null hypothesis. Okay. Then we'll also select alpha. Okay, either provided in the problem or the default value will be 5%. And then we check conditions. Checking conditions is pretty much the same, except for this case, the large sample condition is done a little bit differently. Either there are two ways. The sample is large enough. This is more, okay. Sample is large enough if the population is normal. So if the population is normal, any sample size is large enough, or rule of thumb is n is greater than 25, most cases. So if the population is normal, then any size n is fine. And if the population is not normal, meaning if it's not unimodal and symmetric, then n should be larger than 25. Okay? And then the other ones are, you got big population and then random and independent, right? Okay, but pretty much, again, for the exam questions, the checking conditions is separated from everything else. So those are the hypotheses, okay, and then we'll do some calculations. Okay, calculations go standard error, test statistic, table, right? So we start off, the standard error is going to be S divided by the square root of n. So I guess we can put this 3a. Then we have our test statistic. Our test statistic T is going to be what we observed, kind of the reality, versus what we expected, divided by standard error. Okay, and so this becomes, what we observed was x bar. What we expect is mu 0. We divide by the standard error. Okay, and then we look up T in the table. Degrees of freedom we use is n minus 1. Now the use of the T table is very different from using the Z table. Okay, so I'll just write that. So using the T table is, you know, different from using the Z table. Okay? Very rarely you will almost never get an exact value. You will almost always get a range of values. Okay, so let me just kind of, we'll do one slide just on using the T table. So if you have your T table with you, go ahead and pull that out, and let me find my T table over here. So let's pretend we've done the other math, okay? Let's pretend we've done the math already. Okay, and we'll say degrees of freedom is equal to 10, and my t is equal to 2.51. So we've done the math, and let's say we have degrees of freedom equal to 10, and t is equal to 2.51. Okay, so what I'm going to do is I'm going to just copy kind of this top part right here. Well, I just go to the table and I look up the row for degrees of freedom equal to 10, but just so to illustrate it here. So I'm just looking at this row that says degrees of freedom equal to 10. Okay, and then I ask, all right, where does the value 2.51 fit? Okay, 2.51 fits in between 2.228 and 2.764. Okay, so 2.51 fits there. So this means my corresponding tail probability, and it's technically my corresponding right tail probability, is between 0.025 and 0.010. Okay, so t equal to 2.51 is between t.025 and t.010. t.025 is 2.228 and t.010 is 2.764. So t is between those two values. So the corresponding, what we call right tail probability, I'll just is between 0.025 and 0.010. Okay, we can kind of illustrate this. So the t distribution looks very much like the normal distribution, except it's just a little bit more spread out. And you can imagine there being a cutoff right here, where if I shaded everything to the right, this part is equal to 1%. Okay, this here is 0.01, and then everything to the right of this number, that is equal to 0.025. And the value that gives me 1% is 2.764, and the value that gives me 2.5% is 2.228. And I'm saying I'm coming along and I'm going to kind of draw a value right here at 2.51. And I want to know, okay, how much is to the right of 2.51? Well, I can't give you an exact value, but I do know it's between 0.01 and 0.025, okay? So how much is to the right of how much to the right of 2.51, okay? The exact value unknown. But it is between 0.01 and 0.025. Does that kind of make sense? What's going on there? So basically, when you use the table, you just find your value and you try to see where it's between, and then you go to the column headings and you say, okay, my tail has to be between the values that we see in the column heading. Right. Is that good? Okay, so then let me just, we'll try another practice right here. So let's, so we'll say degrees of freedom is equal to 10 again. So our degrees of freedom is equal to 10. And let's say, t is equal to 4.78. Okay, and so the question is, here we'll make a clicker question out of this, is how much is in the right tail? Okay, or what is the right tail probability? Okay, and your answer choices. Get this started here. Okay, so you can discuss with your neighbors if you need to. How much is in the right tail? What is the right tail probability? If t is equal to 4.78, and you have 10 degrees of freedom. Okay, let's see how you guys responded. Okay, and the correct answer is C. Okay, so the diagram if we take a look at this, okay, well, when we look at the value t equal to 4.78, we see, okay, it is over here, which means our tail must be on this side, okay? And what we notice is that as the critical values get bigger, this is small and this is large, the tail areas, tail is large over here and the tail is small over here. So what the table tells us is that if I draw at t equal to 4.144, the area in the tail, this area is equal to 0.001. Okay? This area is 0.001. And what we're doing is we are drawing a line even farther away. Not at 4.144, but at 4.78. So how much is in this part of the tail? Whatever it is, we know that the exact area of the tail is unknown, but we do know that the tail is for sure less than 0.001. Okay? Because it's even farther away from 0. So when you go to the t table, you're not going to get exact values, but you get a range. Okay, and then sometimes that range is going to be, you know, one-sided. I mean, technically, I guess the other side is that the tail has to be bigger than 0. So there we go. Okay, so that is so that's that. Let me just do a couple additional explanations. So likewise, if we have a value, let me say, let me just copy one more thing here. So let's say we have 8 degrees of freedom, and we have a small test statistic. So let's say, you know, degrees of freedom is equal to 8, and let's say t is equal to 0.74. Then our tail area, whatever it is, must be bigger than 0.100. Okay. The table is symmetric. okay? T-table is symmetric. So even though we only have the positive side, the negative side is identical, okay? The negative side is identical to the positive side. So, let's say we have degrees of freedom equal to 8, and t is equal to negative 0.74, okay? Well, what we do there, okay, is basically we ignore the negative sign, and we look this up, except instead of right tail, we scribble that out, and we say, okay, this is now the left tail, okay? So you just ignore the negative, well, you're not really ignoring it. It's taking into account that you're now saying left tail, okay? You ignore the negative sign, and you look up 0.74, okay? So that's what we did over here. We said, 0.74 is here, so therefore my tail has to be bigger than 10%. Over here, I'm doing the same thing. 0.74 is here, therefore my tail has to be bigger than 10%. And so what we say is the left tail. So over here, this is technically the right tail. And over here, we've got the left tail, whatever it is bigger than 10%. Okay. So it's symmetric. Basically, you don't have to worry too much about the positive or negative signs. It's just whether it's going to be the right tail. If your t is positive, you're getting the right tail when you look in the table. If your t is negative, you're going to get the left tail when you look it up in the table. Okay. Is that good with everybody? Okay, so anyway, we're still in part 3 of our calculation step, right? So calculation, step 3C, look up t in the table, okay? You look up t in the table, so now you have your tail area, and we want to get a p-value. Okay, so the p-value is equal, let me say this, p-value is equal to the right tail area when the alternative has greater than sign. P-value is equal to the left tail area when the alternative has a less than sign. And the p-value is going to equal what? 2 times the tail area when the alternative has a not equal sign. Okay? I'm hoping this part sounds very familiar, okay? Because these are pretty much the same rules that we used when we were dealing with proportions and the z-table. It's just the way we use the table is different, right? With the z-table, you got to get a direct tail area. Okay, now that you have your p-value, step 4 is make your conclusion. Okay, if the p-value is greater than alpha, do not reject the null hypothesis. And if the p-value is less than alpha, reject the null. And everything else that applies. Is that good? Okay. I feel like you guys can do this. I'm going to go ahead and just go straight to hypothesis testing with 2 samples. And then if we have time left over, we can do an example. But I feel like this is Okay, so we'll say hypothesis testing for mu1 and mu2 based on 2 samples. Okay. So part 1, make your hypotheses. The null hypothesis. So when we had 2 proportions, what was our null hypothesis? P1 is equal to P2, or P1 minus P2 is equal to 0, right? Now that we are dealing with means, instead of P's, we have mu. But the hypothesis is pretty much the same. Mu1 is equal to mu2. Can also be written as mu1 minus mu2 equal to 0. The alternative will be mu1 does not equal mu2, or mu1 is greater than mu2, or mu1 less than mu2. Likewise, not equal to 0, greater than 0, less than 0. Okay. That's your hypotheses. Part 2, preparation. Okay, the data needed. You need, from sample 1, you need N1, X bar 1, S1. And from sample 2, you need N2, X bar 2, and S2. Pick alpha, check conditions. Okay, well, once you have that, now we do our calculations. So just like before, we figure out our standard error, then we get our test statistic, then we go to the table. So standard error is going to be the square root of S1 squared over N1 plus S2 squared over N2. Standard error. 3 part A. All right. 3B, test statistic. Test statistic here is going to be T is equal to your observed minus your expected divided by the standard error. What we observed is the difference between X bar 1 minus X bar 2. If the null hypothesis were true, what do we expect this difference to be equal to? 0, right? So we do this divided by our standard error, and this just simplifies then to X bar 1 minus X bar 2 over our standard error. That's our test statistic. And then once we have that, we look up T in the table. Degrees of freedom is equal to n minus 1. Use the smaller n between n1 and n2. And then get your tail area, and then get your p-value. Same rules as before. I don't think I need to rewrite all of those. If the alternative has a greater than sign, it's the right tail area. If the alternative has a less than sign, your p-value is the left tail area. If you have a not equal, it's 2 times the tail area. And then the last part, make your conclusion. And I don't know if I need to write this again, but sure, I will. Okay, and if the p-value is greater than alpha, do not reject the null. And if it is smaller than alpha, then you do reject the null. Okay, I guess we got time for an example. So let's try one out. Okay, and if you have the formula sheet, everything's written in kind of those bottom two boxes here. Okay, so let's do an example. I will not tell you if this is dealing with one sample or two samples. You'll have to figure that out. And okay, so we'll say in 2010 I don't know, maybe we'll do 2015. Okay, in 2015 we surveyed we'll say 25 people. We asked how many text messages do you send a month? Okay, this will be 25 randomly selected people. Okay, I have no idea what text message usage is across the nation. I have no idea. But we'll say the mean was, I don't know, 185 texts, with a standard deviation of 62 texts. Okay, it's probably very right skewed, would be my guess. Okay, and then we'll say in 2017, we surveyed, we'll say 30 random people. Okay, same question, how many texts? The mean here is 203 texts with a standard deviation of 68 texts. Okay. All right. So the question is, does our evidence, or I'm sorry, does our data provide evidence that text messaging rates, I don't know, whatever, have changed in the last 2 years, have changed between 2015 and 2017. Okay, we'll go ahead and get started. Let me see if I can make a clicker question out of this, and when I come up with a good clicker question, I'll put up the answer choices here. But you should be able to get started as far as things to do. Okay, this will be your clicker question. I'll say, what is the resulting p-value? Okay. A is p-value is equal to that. B is the p-value is greater than that. C will be the p-value is greater than that. And we'll say D we'll just do that. Okay. So those are your answer choices. Pick the best one, okay? Choose the best, not the. Oh, sorry, I gotta start the clicker. Okay. Okay, so what we'll do is I'll go ahead and I'll just identify all of our numbers here. Okay, so this will be, we'll say 2015 we'll call sample 1, and 2017 will be sample 2. Okay, and thus 25, this is N1. N1 is 25 and N2 is 30. Okay, 185 will be X bar 1 and 62 will be S1. Over here we've got 203, which will be X bar 2, and 68 will be S2. Is that okay? So keeping all of that together in our head, all right, here I'll just write this. Okay, we got X bar 1, S1, and N1, X bar 2, S2, and N2. And let me just flip back. I got 185, 62, 25. And then I've got 203, 68, and 30. All right, hang in there. Okay, so what I've got to do, our null hypothesis, when we set this up, is going to be that mu1 is equal to mu2. The alternative is going to be that mu1 is not equal to mu2. The reason for the not equal sign is because right here it says has changed. Okay? If it was different, that would be not equal. Changed would be not equal. If it said something like has messaging rates increased, then we would have a less than sign because that means sample 1 is smaller than sample 2. Or if it says has decreased, then that means sample 1 would be larger than sample 2, or something like that. Okay? So we start off there. Our standard error is going to be the square root of 62 squared over 25 plus 68 squared over 30. When I punch this into my calculator, 62 squared over 25 plus 68 squared over 30, I get 17.547. Okay? Therefore, my t is going to be x bar 1 minus x bar 2 divided by the standard error. So I'm going to have 185 minus 203 divided by the standard error 17.547. When I punch this in, I get negative 1.026. Negative 1.026. So I come to my table and I have 24 degrees of freedom. 24 degrees of freedom. I go to the table, 24 degrees of freedom. And the first value I see is 1.318. And that corresponds to 0.100. Okay, I'm going to stop the clicker thing, so get your clicks in if you haven't done so already. What's the answer?
What were the choices?
What were the choices? Oh. It was B is p-value is greater than 10% and C is the p-value is greater than 20%. Okay. What are we supposed to pick? All right. Well, I'll just let it keep running. Okay. The answer is C. Just put in C. All right. So we ignore the negative and we have 1.026. Sorry, the tail is right here, and this means what we do is we change the title to left tail area, okay? So the left tail is going to be greater than 10%, 0.10, because the alternative has a not equal sign. Our p-value is equal to 2 times the tail, so therefore our p-value is going to be greater than 20%. So your answer choice is C. Okay, so we'll go ahead and stop there, and we'll see you guys on Wednesday.